currently, these kinds of secure data collaborations, they've been performed through human-in-the-loop. I like to point to how a lot of our, for example, secure query capabilities, instead of flying somewhere to access data and process our data, you can kick off a query, take a sip of your coffee, and get a result.
What if you could perform complex computations on sensitive data without ever decrypting it? That's the promise of Fully Homomorphic Encryption, or FHE, and it can have post-quantum protection by design. Use cases range from accelerating rare disease research to detecting international financial crime. And it can even safeguard AI workloads. We talk all things FHE in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the co-founder and CTO of Duality Technologies, Dr. Kurt Rohloff. Welcome to the show.
Hi, happy to be here. Thanks for having me.
Yeah, thanks for coming. In addition to being in quantum for a very long time, I've been involved with cryptography for a very long time, even longer. So I do tend to nerd out on these topics. So you're kind of a natural fit. So can you start by giving our audience a high-level overview of homomorphic encryption? Many of them might not have heard of it.
Sure. No, happy to. This is a topic I've been working on for a good 15 plus years and always happy to kind of share with the community what we got going on in the space. So homomorphic encryption is this wild capability where you can compute on data while it's encrypted. And so you're probably familiar with other kinds of encryption like RSA and AES and elliptic curve and kind of things like that. These data formats, data encryption technologies, they're wonderful for protecting the confidentiality of data. But the challenge of these encryption technologies is that if you want to actually compute on the data, do any manipulation of the data, run some analysis on the data, you can't do it unless you expose the data to where you're doing the analysis. And so the great benefit of homomorphic encryption is that you can take data, encrypt it, upload it to a place like an Amazon cloud, and then run analytics on the data while it's still encrypted, and basically get end-to-end protection of your data. So we have not just encryption at rest, not just encryption in motion, but also encryption in use, which I am just super excited by as a co-founder.
Yeah, and people are used to this idea of having a private key and a public key and things like that. Well, here, of course, the interesting aspect is the person who creates this bit of data has that private key, sends the data out there, and then I guess other people can sort of compute with it and then send it back, but never actually able to read it or understand what was inside. So and of course, there's 3 different levels, right, of what you can do to that kind of data.
Yeah, there is. There might be actually a few different things you're talking about. This technology is wonderfully malleable, where you can do things like outsourcing computation. You can actually even doing things like encrypt queries and run encrypted queries on data so you can protect what you're asking about. You can also mix data from multiple places and kind of bring it into a central spot and then do that. But there's also kind of different versions of how much computation you can want to run and how much you want to enable. There's been very well-known versions of this technology where you could do just additions. For example, adding a lot of numbers. And sometimes that's really important for things like vote counting and stuff like that. Other times there's another kind of homomorphic encryption called somewhat homomorphic encryption, where you can do computations of a certain complexity up to a certain point. And that's great if you want to run, for example, like a specific regression model on data. You don't want to run a model on data to do some sort of triage about whether someone is, have symptoms indicative of a certain disease or certain kind of other kind of bad incident. And then, of course, you have what they call fully homomorphic encryption, which is the ability to run arbitrarily complex computations on the data while it's encrypted. And so the pie in the sky is for example, training machine learning models on encrypted data. And that's like a super important thing where, for example, you can take data from multiple cancer research centers across the US and train better models to identify certain kinds of rare diseases that you wouldn't normally be able to identify unless you had data from multiple research sites, for example.
Excellent. Like you nailed two of my next questions in a row. That's perfect. Yeah. So listeners, just to understand that there's different levels of also how many computations you could do and types of things you could do with it. And of course, as that goes up, sometimes it leads to more overhead, right? More complexity, computational like drain, and becomes slower or more, power hungry.
Yeah, no, that's a great point. One of the kind of the core concepts of this homomorphic encryption, one of the reasons it works is, or how it works, is you basically have some kind of core data, and the encryption mechanism is basically just hand waving a bit, embedding that data in a bit of noise. And so you basically have something that's very much looks like, random numbers and kind of everything else, but there's like a seed of data that's embedded inside there and hidden through the encryption mechanism. And of course, when you need to run computations on this encrypted data, you basically have to do the processing on all of the noise, not just the core of the data also. And so this causes overhead. And that overhead can computational overhead can vary wildly across the depths of computation that you want to run. And some things that might seem complex, like for example, manipulations of matrices and vectors of data, are actually still kind of actually not that complicated with a lot of this homomorphic encryption stuff. Sometimes things that look relatively straightforward, such as for example, natural text processing, that's actually fairly complicated in the space. And there's a lot of really just wild design trade-offs that kind of come into how you want to rethink how you encode data, how you compute on data, what kind of algorithm design you want to have to basically make this stuff run efficiently. And in my role as kind of technologist and as CTO, a big chunk of my professional life for over the past decade has been how do you design technologies, how do you design products that use this homomorphic encryption for data collaboration and still have a lot of efficiency that makes this stuff practical and commercially viable also at the same time.
So by now, people are hearing this and thinking, "What does this have to do with quantum?" And I guess it's time to introduce that. So how is this relevant in a post quantum world? To use the name of the show, kind of
Right.
right in there.
Well, one of the nice things about the core fully homomorphic encryption schemes is that they're all lattice based. As you're probably familiar with some of the NIST PQC standards, is that they are there are several of the kind of the key schemes are also lattice based. The fully homomorphic versions are slightly different. They're based on ring learning with errors, which is a kind of a core mathematical hardness property that the cryptography is built on top of. It's similar, but very similar, but a little bit different from the PQC standards. But it does have these really nice quantum secure properties associated with them, hence PQC. And so that's been really great for us in that, what we found is that when we went to market, there was kind of this dual kind of purposes where a lot of CISOs were kind of very, very open, in fact, even very receptive to using our product. One, because, there's the value add of kind of, computing on data while it's protected, but also because they wanted to have a lot of experience, want to build up institutional experience with using post-quantum crypto technologies before it was mandated by regulators and policymakers and government and so forth. And we're very, very happy to oblige. And so, I know there's been a few kind of large organizations where we've been basically the first to deploy post-quantum crypto in their tech stack also.
Yeah, if you're going to introduce some kind of new cryptographic product or service, coming out of the gate with it being PQC right now is obviously a way to go.
Yeah,
Yeah, it's going to be an easier sell. And what on that topic, what does this product really look like? Like what are you providing right now in the
sure.
real world besides the papers and theories?
No, no, for sure. Yeah, existentially, we're a software product. Duality Technologies is a software product company. And one thing I would love to highlight, especially given the post quantum nature of this podcast, is our core cryptography is all open source. It's in this open source library called OpenFHE, fully available on the internet. We have a wonderful community with an online forum, discourse forum, and things like that, which we love to have folks participate in. And the technology is all export compliant also, which means anyone in the world can download it on the internet and use it and everything else, which is great. Transparency basically breeds trust, which we love, and we love to be transparent to kind of build trust in the capabilities that we're building out. What Duality does is that we build products that leverage OpenFHE, and several products use other privacy technologies too, but we use this open source FHE and kind of wrap it in an ecosystem for secure data collaboration. And existentially, yes, we love homomorphic encryption. We've been pushing it forward. Our core team's been pushing it forward for a very, very long time. And we love to build products that enable secure collaboration on very, very sensitive data. And that could be a few different things. We have one product called Secure Query, where we can actually take a query and encrypt the query and send the encrypted query to a third-party data source. And this, for example, lets you ask questions what you don't want to reveal what you're asking about. And so this basically allows you to kind of, pull in data and pull in intelligence without necessarily having to do a bulk upload of data, which is really nice for some regulatory obligations in some industries. Another area where we are often used is in areas such as public health. Like I said before, this notion of a rare disease is especially prevalent. Now, the concept of rare disease, and I'm going to get it slightly wrong, so please bear with me, is a disease that affects 1 in 10,000 people or less. The challenge with being in a very large country like here in the United States is that rare diseases are surprisingly common. I think it was something like 10% of the population is affected by a rare disease at some time in their life. And the trouble with these rare diseases is that they are underserved by medical treatments. And that's for a few reasons, partially driven because clinicians, doctors, medical researchers can't classically have not been able to aggregate enough data to actually get insights onto these rare diseases. And so we basically provide software for medical professionals to basically be able to aggregate data and then compute on that data to generate medical insights relevant to rare diseases and things like that also.
So this kind of system remains fully end to end, right? It's sort of like, I'm trying to visualize it for listeners. Is there kind of a client piece that it encrypts and then it goes out, so there's no chance of it being sent some insecure way first and then becoming secure later, right? It's from end to
Right.
end.
No, that's a great question. And we have a few different deployment models,
Hmm.
apropos of what I said before, being very malleable. Like, for example, the secure query, we have a query client that someone could come, go and install on their laptop or phone or wherever, which would take a query, generate a key, encrypt the query with that key, send the encrypted query off to the data source, and then we have basically a server side bit of software that basically sits where the data is, takes the encrypted query in, runs the analytics on the data using the encrypted query, generates the encrypted result, which then gets sent back to the client and then decrypts, and using the key that's stored locally. And we also have similar versions for when you want to have these secure, like medical collaborations, where you have basically data clients at each of the data providers. You might have like a server-side data that might reside at some cloud, where it actually does the processing and things like that. And you also have a key management framework that actually hold the keys and manage the distribution of, for example, public keys and stuff like that also.
So you hinted at it a little bit earlier, but have you actually used this then for some kind of AI model training in the real world?
Oh, that's a great question. My colleagues here at Duality recently put out a series of demos at one of the big crypto conferences called Crypto in Santa Barbara. And at the privacy preserving machine learning workshop, gave demos of our ability to basically encrypt FHE protect inferences on LLMs. And so, for example, you have a query for an LLM, we have the ability to basically take that LLM request, encrypt it, and then run it through, admittedly, older versions, but basically versions of BERT. And so we're very proud of that. And IEEE Spectrum just had an article on us just last week, actually. We're very happy about this work. We're really excited about the possibility of these secure data technologies to basically secure the AI tech stack.
So for that use case, it wouldn't be technically the training, it would be the inference part where you're asking a question of the,
Yes.
yeah.
Yeah. So yeah, there's we see a lot of needs for different kinds of protection of workloads in the AI space. There's the protection of the query, where sometimes you don't want people to know what you're asking about. For example, you're running a model in the cloud and you're running around with a mobile device. Sometimes it's RAG, retrieval augmented generation, where you want to basically upload files to basically help with context for LLM type operations, and you don't necessarily want to reveal the files that you're providing for context. And this could be things like financial documents or contracts or other kinds of proprietary IP in a white paper, for example. And of course, there's also training about how you can take very, very sensitive training data and do the analytics to basically train your own LLM on this data also, or tune or retrain to also.
So anytime AI comes up, you start to think of power, computation, overhead. They're literally building nuclear power plants and putting them next to the, AI centers. So what kind of, to make it a little simpler, what kind of scalability challenges do you see with FHE in general? Like, is it creating any kind of overhead that's becoming unreasonable at certain
Right.
scale?
So I often like to think about what we're replacing. So currently these kinds of secure data collaborations, they've classically been performed through human in the loop data use agreements, memorandum of understanding, NDAs, things like that. Things where lawyers have to bang out legal agreements and then get them signed. And these things could take days, weeks, months. They could be take quite a bit of cost, and often they're one-offs and not really all that scalable because you're basically limited by the time of your legal budget also. And so this has also been prohibitive in terms of the kind of democratization of science and kind of sharing of data, and that large organizations, large hospital systems have the ability to kind of spend money on budget for lawyers. Smaller organizations, tribal health centers, really not so much. And so what this does is these secure data collaboration technologies open up and democratize the ability to do science, democratize health, and basically make health more equitable and make research more efficient and make science more efficient also. And you are right. There's no free lunch, and basically what you're doing is that you're shifting the scalability bottlenecks of legal agreements and moving them over into compute cost and compute overhead and things like that. And I like to point to how a lot of our, for example, secure query capabilities, they're what I like to call a cup of coffee time. Instead of flying somewhere to kind of go and access data and process on data, you can kick off a query, take a sip of your coffee and get a result, which is pretty awesome, I think, in that way.
Mm-hmm.
And think of all the greenhouse gas that you're saving, flying people around to kind of do those things, and let alone time and cost associated with that too.
Yeah, that's a super strong point because this isn't just accessing a piece of information. This is doing things that might not have ever been possible without FHE, right? The types of protections and systems in place. So if you're into threat modeling or anything like that, you start to see why systems like this are so much simpler. There's fewer points of fewer data boundaries and things where sensitive information can pass and be leaked and all that kind of thing. Yeah, that makes really great sense. So there's no real limitation, right? You could, in theory, put this on cloud workloads. It's just you're going to be spinning up more resources, right?
Yeah, no. So the kind of the theoretic way of saying it is that the fully homomorphic encryption is Turing complete. You can do anything you want on it. It's a circuit compute model. So the execution model is a little bit different from if you're, for example, used to programming in Python or Java or something like that. It's more like programming with a circuit board, like an FPGA or something like this. And there are costs, and so it's not a panacea. It won't solve all problems. It's a confidentiality, protection tool. But there's some times where just the workloads are just too high. But what we're focusing on is how do we basically enlarge that bubble of things that are reasonable and feasible with these kinds of technologies. And it's been my life's work. I've been very happy to kind of push it forward, and I'm really happy about how far we've come to basically make data collaboration that much more secure and that much more quick and that much more efficient also.
So assuming, I guess the goal might be ultimately to end up in the marketplaces, right? like you're using AWS or Azure or whatever, and you're just like, oh, I want to use FHE, ta-da, and you click it. So let's say we get to that place where it's so commonly accepted. And it might be because right now people are going to be more cryptographically open to new ideas as PQC becomes a new idea in itself that everyone has to deal with. What, let's say, top 3 or 5 like use cases, what would you think that people would be most excited about? If they
Sure.
saw that, what would this enable?
So I'm a big fan of any. So first off, let me probably dial this back a little bit. Where I see kind of like the main immediate usage of these kinds of technologies, and not just homomorphic encryption, but secure data collaboration, is anywhere where there is regulated data, where there's value from collaboration, where there's basically knowledge and insights that could be gained from bringing data together. But there's also legal protections on sharing data, apropos what we call regulated data industries. And so this is finance, healthcare, government, education, insurance. There's kind of a few of them that are fairly well known. Where I see some of the biggest usage is in, for example, financial crime. Banks, individuals, governments, we lose a lot of money in insurance. We lose a lot of money every year basically dealing with folks who basically run scams, pull out data and exploit, for example, elders or other folks and run phishing attacks and stuff like that. Wouldn't it be great if these, erstwhile competitors, the banks, could securely collaborate to identify amongst themselves, without necessarily government intervention, identify amongst themselves who is potentially perpetrating these kind of bad financial crime acts. And so I see a lot of value for that in terms of reducing financial crime. You can also think about it being applied for things like cybercrime, where you might be able to kind of see someone operating across a network, and if organizations could collaborate, banks or factories could collaborate to kind of share network trace data and have a better view of what kind of bad behavior is propagating against their network without necessarily revealing their sensitive information. I see this as basically kind of another way of helping to address other kinds of distributed criminal networks also.
Yeah, and Europe should be all over this, right? They don't let you do anything there, basically. So I would think that FHE would be perfect
Yeah.
when it comes to handling data.
I often think about the Goldilocks model. Like you need in some sense, you want people to kind of trust each other enough to want to collaborate, but you don't want them to trust so much that it's actually very rare for someone to trust so much that you can reveal everything that you have. And so it's like this kind of like, hey, we want to get together, we want to do something together, but I really can't quite share everything. And that's like, I think that's like a 90% problem. It affects the 90% of or more of situations. And I'm very happy to provide a solution to kind of address that wide swath of data collaboration needs also.
Yeah, it should enable, like we talked about earlier, with things that couldn't have been possible without flying someone somewhere. It should
Yeah,
enable like a much tighter, fewer points of failure kind of solution for how data moves around and gets encrypted, decrypted, all that, kind of minimizing that is a good thing. And that would make it in general less susceptible to something like harvest now decrypt later, because you're
yeah,
not going to be able to capture these packets. They're not being, like sent out in any other way. So, how do you feel in general about the state of the industry when it comes to HNDL? Like how do you see that whole process going? And are there ways that maybe you can try and convince certain use cases to migrate to FHE to also help prevent that?
right. So I spent the vast majority of my career in support of an organization called DARPA, which basically develops advanced technologies and tries to transition them out into the world to kind of do good. And a big part of that community is often thinking about like who are going to be the first users of new technologies. And I've kind of developed this attitude of, you develop some really cool new stuff. You want to make it as boring as possible. You want folks to kind of use it and not necessarily disrupt how they're operating, what they're doing, what their business processes are, hence the boring part. And I often look for scenarios where users are already collaborating, but there's friction and there's extra costs associated with these legal agreements and things like that. And I'm not at all saying, like ignore the lawyers and don't pay attention to that. And I'm basically saying like, hey, let's embrace that process, but let's make it more efficient, and by reducing risk and reducing liability by using these secure data collaboration tools and technologies. And so I often think about places where folks are already sharing data. They've already kind of crossed the threshold and know the value proposition of that data, but they also already know the costs of sharing that data, apropos of the legal overheads and things like that. And how do we basically provide very well-defined ROI of reducing that legal overhead also at the same time?
Yeah, and you're also preventing keys from moving around as often in general, which is
Oh yeah.
always a good thing in security. You don't want your symmetric keys.
Never move decryption keys.
Yeah, you don't want them floating
Yeah.
around in the world. So that alone makes FHE pretty awesome, I've got to say. And I love how you name dropped DARPA in there, like it's this like tiny little, mom and pop shop. I worked for this little startup once before. That's kind of funny. Yeah, I think everyone obviously knows about them. So on that adjacent topic, this has to be of extreme interest to government use cases, right? I would think FHE.
Yeah. Yeah, it is. We pushed for the open source technology to have this, OpenFHE, the open source library that I co-founded with my research partners. And it's been kind of amazing to kind of see the uptake of this technology over the years. And you can think about all different kinds of use cases where you can use this, where there's clear societal benefit. Anywhere from public health scenarios, like I addressed the kind of the rare disease analytics and things like that, where there's issues of how can we basically help not just American citizens. I happen to be in the U.S., but help people across the world be more healthy and develop better medical treatments and that. And that's a very, very clear win in my opinion. The other is I kind of go back to what I said before about financial crime. Criminals know no boundaries, and transnational financial crime is a thing, and it's a thing to basically track. And it's one thing when you have competitors like Wells Fargo and Bank of America, like they know each other, they kind of trust each other if they're really competing. It's one thing to get them to compete. It's another thing to get Bank of America with some random bank in Central Asia to collaborate to identify perpetrators of financial crime and things like that. Not just kind of the trust issue, but also the regulatory issues of kind of sharing data across international boundaries and medical data across international boundaries. And so, yes, the government, I think governments for good reason have taken, a fair bit of interest in these technologies, particularly for the benefit, very, very clear benefit to their citizens of how this basically helps people live more healthfully, be better protected from crime, and just help governments be better governments in those regards for their citizens.
Yeah, and I like the open source approach. We're seeing PQC in open source. Obviously, it's an OpenSSH, it's an
Yep.
OpenSSL. It's a real thing, and is part of the hope that people will use this in their own apps, maybe open source free apps, whatever, and then encourage the industry to be constantly looking at this and helping you with bugs or whatever. Is there some of that as like a little ecosystem built up already that you have in place?
Yeah, no, there is, and that's a great question. There is quite a bit of an ecosystem. I knew there are still other startups that are using the open source library, which I couldn't be happier about. Provides not just validation, but also helps with things like testing and documentation and very much a community effort. And there's also an ecosystem growing around hardware acceleration technologies and things like that. Like we talk about overhead. I'm aware of several startups that are designing ASICs of different special hardware processors to make these things run faster. I'm aware of several large tech companies that are also doing research in the space too, in terms of plugging either commercial off the shelf or special processors for doing these kinds of things. And there's even kind of upstream work being done at other tech companies that look at how you can basically automate the compilation of programs to run on top of FHE. Some of the big names that you might hopefully very familiar with is, for example, Google's been doing a lot of work on FHE transpilers. Intel's been doing a lot of work looking at hardware acceleration of FHE. And like I said, I could rattle off a few other names too. But yeah, it's been really wild to kind of see the kind of the growth of the ecosystem around FHE in general and this open source library, OpenFHE in particular also.
Yeah, acceleration hardware is key. I mean, who knows? This could end up even on IoT devices one day, doing some kind of counting or
Yeah,
surveying of some types of information. And if it's government, it'll be scarier sounding than that. But whatever it'll be, but yeah,
yeah.
acceleration is key. So that's great. It sounds like you gave a lot of thought to the ecosystem. So I was always big into open source and Linux and things like that. So yeah, it's kind of fun to see this growing that way too. So before I let you go, is there one big push, like one big kind of either use case or headline that you'd like to see next year for FHE?
Wow, that's great. If you're going to ask me what I would want to kind of share with your audience, I would open invitation for engagement with the OpenFHE ecosystem.
Hmm.
Check it out, kind of use it, poke at it, join the forums, ask questions. But in terms of where the technology is going, I'm really excited about the protection of LLM workloads.
Hmm.
I'm really, really happy about our team's recent result that IEEE Spectrum just wrote an article about how we're basically protecting LLM workloads with FHE. I think that's a really exciting advancement, and I really want to see much more of that, both in terms of more complex queries, more complex operations, engaging with the hardware acceleration capabilities to make it go faster, and also how we can kind of broaden out the footprint in the AI space with FHE-based protections also.
Yep, that's great. There's quantum for AI, so why not a type of PQC for AI too? That sounds terrific. So Kurt, thanks again for joining.
Thank you. Happy to be here.
That does it for this episode. Thanks to Kurt Rohloff for joining to discuss duality. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on X and LinkedIn. Until next time, be kind and stay quantum curious.